certain reagents. So the particular reagent that we chose was copper. The reason is because of this well-known copper catalyzed click chemistry. This is a very unique chemistry in that these two functional groups in aqueous solution at room temperature can be quickly catalyzed by copper to form this tethering. So this reaction has been used to tether a lot of these molecules together. But our thought is to actually use this reaction to detect copper. The design is to actually put these two ligands on the surface of different gold nanoparticles, and if there is presence of copper, because of the reaction that would tether the gold nanoparticles together, and because at very low densities or concentrations, gold nanoparticles, depending on whether it's dispersed or it's aggregated, the color is very different. Dispersed gold nanoparticles are typically this pinkish color. Aggregate gold nanoparticles in aqueous solution is typically bluish purple, or if it's completely aggregated, you get a clear solution with precipitate on the bottom. So our thought is to use this to detect copper because it's very selective. Only copper is known to catalyze this reaction, and also because copper is used as a catalyst, so a very small amount of it could catalyze this reaction, so that may potentially lead to high sensitivity detection. So my student Zhou Yang actually took a lot of time to synthesize these molecules to put on the surface of the gold nanoparticles, and finally we came up with ones that would actually work precisely as we had anticipated. That is, without the addition of copper, the solution, the aqueous solution is pinkish. With the addition of copper, we get aggregation as a result. And this reaction is extremely selective because only copper catalyzes this reaction. We can put high concentrations of mixtures of other types of ion in, and they would all look like that. Also, in terms of a detection limit with naked eye, we could go to sub-micromolar. So that's, I think, already a record for detection of copper without using advanced instruments. So after this, we have been thinking about how to generalize this approach and make it more useful for other types of detection. And one of the areas that we have been very interested in is to detect different types of proteins. And I think the most popular, most commonly used assay for detection of proteins is this immunodetection, where you have an antigen that's immobilized on the surface, and then you go in with the primary antibody that recognizes the antigen, and then the secondary antibody that's typically fluorescently labeled or labeled with an enzyme that changes the color of the substrate. So the production of fluorescence or the production of a color would tell you if any of these antigen or antibody is around. So that could be used to detect either the antibody or the antigen. And also coupled with this 96-well assay format that allows you a fairly high throughput assay that can look at multiple reactions and interactions and multiple conditions and dilutions. So this 96-well based immunoassay is actually one of the most popular assays for protein detection. So our thought is actually to use copper to indirectly detect the antigen or the antibody. So instead of using a secondary antibody that has a fluorophore or an enzyme labeled secondary antibody, we use a copper oxide nanoparticle labeled antibody. So after all this primary secondary antibody recognition on the surface, we can wash off everything else in the solution. And if this reaction indeed took place, the copper oxide nanoparticle will remain on the surface. And then at this stage, we can add in dilute hydrochloric acid to wash out the copper ion. Then we can carry out the detection of copper, as I just described, using the mixture of gold nanoparticles that are functionalized with these ligands for click reaction. So the advantage of doing this is because the copper-based assay has very high sensitivity and selectivity based on the unique chemical property of click chemistry. So this actually translates into fairly high selectivity and sensitivity for the antibody antigen recognition reaction. We have actually carried out quite a few different model assays that I'll tell you a little bit about just one of them, where we are carrying out an HIV assay for the detection of the HIV antibodies in patient serum. So these are real patient serum samples that we obtained from the Chinese Center for Disease Control and Prevention, where the wells from C1, C2, and C3 have this confirmed positive blood serum, and C4 has confirmed negative blood serum, and C5 and C6 are negative controls. So as you can see, only the wells that had these HIV positive serum samples had color changes to purple or blue, whereas the negative serum sample or the negative controls all keep the gold nanoparticles in the original pinkish color. So we can actually also look at the the sensitivity of the assay. We can actually serially dilute the serum sample to look at what stage the signal turns negative. So we actually compare this with fluorescently labeled and enzyme labeled secondary antibodies, and our results show that that the copper-based assay is actually more sensitive. In some cases, close to an order of magnitude sensitive than commercially available assays for detection of proteins using secondary immunoassays. So we think this types of assay will be very useful for detecting particular types of proteins in biological experiments. And also with the improvement of the technology for antibody engineering, people have started to be able to detect many small molecules using antibodies. So we think that this technology can also be used in that area. So the next example that I want to give you is an assay for quantifying protein in aqueous solutions. So protein quantification using instrumentation, I think, is there are many choices and fairly straightforward, but without having to resort to complex instrumentation with fairly high accuracy is still a big problem. There's actually a few assays, such as BCA assay, the Bradford assay, that allow us to use visual readouts for protein quantification. So one of them actually